Okay, right, you should have got back your graded first assignments, and I'm sure if you've got them back, you've probably tried to go through them and see how the grading was done. Now, there is a solution set that's posted on the web, so you do want to take a look at the sample solution set, compare that with the answers you gave. Now, if you're not happy with the grading, what you want to do is you want to first talk to the grader, this Mr. Liu, and see if you can resolve your differences with him. And if you can't, then please bring the material to me and we'll go over it, and we should be able to resolve it at that time. Okay. Now, again, there is an exam scheduled for Friday. The exam is structured quite like the sample tests that are there on the web. And we do plan to give you about 60 minutes to do it. So you want to be sure that you get here on time and that you can, in fact, spend a few minutes extra. Now, you don't really need 60 minutes. As I said before, if you have prepared for it, you should be able to do all the problems in 50 minutes or a lot less than that. If you haven't prepared for it, 60 or 90 minutes are not going to be enough to do it. So I don't really think anybody's going to be here after the 50 minutes, but just in case, the intention is to let you hang around if you do want a few extra minutes. Okay. All right, any questions? All right, so today we're going to take a look at the last structure we're looking at for single-ended priority queues. This one was called a pairing heap. Now, the pairing heap supports all of the operations supported by the Fibonacci heap. And if we compare the Fibonacci and pairing heaps, first with respect to their actual complexity, okay, we see that as far as the actual complexity is concerned, the pairing heap seems to have a better actual complexity for the decreased key, which is order 1 instead of order n. And then the actual complexity on the remaining operations is the same as that for the Fibonacci heap. Okay. Now, a comparison on actual complexities is probably not a very worthwhile comparison because we know the Fibonacci heap is lousy as far as actual complexity per operation is concerned. And really the same is true for pairing heaps. If you have an actual complexity of order n, that's not a great thing for an operation. Okay. The merit of the Fibonacci heap is really because of its amortized complexity. So let's take a look at that comparison. Okay. So as far as amortized complexities go, the best bounds that are known for the amortized complexity of the pairing heap operations are actually log n for each one of them. Now, it's not known that those are tight bounds, so maybe somebody can prove better bounds, but what is known is that there's no way you can achieve the bounds of the Fibonacci heap. So there are lower bounds on the amortized complexity of pairing heap operations, which essentially say that if your amortized complexity for insert is order 1, well, then you can't have I mean, if you make this thing order 1, then you can't have the same numbers on that side. Somebody's got to be bigger. Okay. So, as far as proving complexities is concerned, the upper bounds of that are the log n that's known. There are lower bounds known, which show that the pairing heap cannot match the Fibonacci heap from the amortized complexity point of view. Okay. Now, if you know that, then you might say, well, why bother to look at the structure? Okay, since it's provably inferior. The reason is that this is probably one case where one has to go back and take a look at the meaning of complexities and realize that if you have some algorithm whose complexity is, let's say, order of n, you got another algorithm whose complexity is order of n square, it might just be that for all practical cases that you want to solve, the order n square is better than the order n because of constant coefficients that are multiplying the n and the n square. And that's what turns out over here, that The experimental studies that have been done using pairing heaps versus Fibonacci heaps in places like Dijkstra's shortest path or Prim's greedy spanning tree algorithm, those indicate that if you use pairing heaps, you actually get reduced runtime compared to using Fibonacci heaps. So working with large graphs, it just turns out that because of the simplicity of the pairing heap, even though it's asymptotic, the asymptotic bounds on amortized complexity are not as good, it happens to give better performance. Okay. So something to keep in mind, analysis has limitations. Okay. So let's take a look at the pairing heap. It's simpler to implement. That in part results in its having better observed runtime. And it's more space efficient. The total number of nodes used is the same, one node per element, but the number of fields in a node is smaller. Okay. So experimentally you have better runtime, and it's easy to see theoretically that the space is less. All right, so definition. Again, you have two types of pairing heaps. You have the min and the max, depending upon whether you want a min priority queue or a max priority queue. And it's basically just a single tree. Okay. Whereas a Fibonacci heap was a collection of min trees or a collection of max trees, here you have a single min tree or a single max tree. Okay. We'll take a look at the max version. So far we've been consistently looking at the min, so I'm going to make a switch here and look at the max version. Okay. Doesn't really matter which version you look at, they're pretty much the same. All right, so I got a max tree here. This is a candidate for being a max pairing heap. The node structure we're going to adopt, each node is going to have a child pointer, which will point to the first child from amongst this list of children. We're going to have left and right sibling pointers, because we're going to keep the siblings in a doubly linked list. This will not be a circular list, though. It will be simply a doubly linked list. Since it's not a circular list, the left sibling pointer of the first node serves no useful purpose. Okay. I mean, it would normally be null because there's nobody on its left. We'll find a better use for it than setting it to null. Okay. Similarly, the right sibling pointer of the last node serves no useful purpose. It's null other than telling you it's the last node, but we're not going to find any other use for that. Okay. All right, so the left sibling pointer of the first node, instead of being set to null, is actually going to be used to point to the parent. As a result, we're not going to have parent fields. Okay. Only one node will point to the parent, and that's the leftmost node. Okay. The remainder won't. We'll be able to tell if you're sitting at the first node. Okay. If you look at its left child, if you look at its left sibling pointer, if it's the first node, the left sibling pointer should go to the parent, and then the child pointer of the parent should come to the first node, so it should come back to this fellow. Okay. So if you perform this check, okay, so x dot left, that gets you to the parent, supposedly, if it is the leftmost fellow, and then you follow the child pointer on the parent. If it gets you back to x, then x was the leftmost node. If it doesn't get you back to x, then you were not at the leftmost node. Okay. So you don't really need to have a null pointer in the left field of the leftmost node to tell that you're at the leftmost node. Okay. All right, so we're going to use the left pointer in the leftmost node really as a surrogate parent pointer. There'll be a data field which keeps the element. Okay, and that's it. Okay. So we're going to have these four fields: a data field, left and right sibling fields, and child. Okay. The fields we're saving compared to a Fibonacci heap, we're saving the parent, the degree, and the child cut field. Okay. So there's a reduction in about 3 fields. Okay. As a result, the total space needed by pairing heaps is less. Okay. All right, let's see how we perform the various operations. Okay. Again, we're only going to look at how the operations are done. I'll be able to establish the actual complexity of the operations in class. We will not go through the amortized complexity analysis. Okay. All right, the key operation in pairing heaps is the meld. Okay. So in a meld, you're given 2 pairing heaps and you need to combine them into one. Okay. And that's done using something called the compare link operation. And what you do is it's a lot like combining 2 trees of equal degree in the case of Fibonacci heaps. Okay. Except that here the 2 trees may not have the same degree. Okay. So compare link is done on 2 trees whose degree may or may not be equal. What you do is you compare the 2 roots, and since you want to build a max tree, the fellow with the smaller root becomes the child of the fellow with the bigger root. Okay. So if you have this as one of your max trees and you have that as the other, we'll compare the 2 roots. This fellow is smaller, so this needs to become a subtree of the 9. Okay. And it will become the leftmost subtree. So it's pretty much the same as what was being done in the Fibonacci heap when you'd combine 2 trees together. The only difference is that here the degrees of the trees may not be the same. Okay. All right, so as far as melding 2 trees is concerned, it takes you only order 1 time to do it. Okay. You do the comparison, and then this has to join the doubly linked circular list here as the leftmost fellow. Okay. And that's quite easy to do. You need to change a child pointer. Using the child pointer you can get here, and then you can insert it at the left and set the appropriate parent pointer back. Okay. The parent pointer is in fact the left sibling pointer. All right, so any questions about the meld? Okay. It's an order 1 operation. So look at insert, very much like how you might insert in a Fibonacci heap. You create a 1 element max tree like you would out there, and then you do a meld. Okay. So if that's my existing max tree of Fibonacci heap, I want to insert a 2, I'll create a node that has the 2 in it, and then do a compare link operation. Okay. So since 2 is smaller than 9, it'll become the leftmost child of 9. So you create a single node pairing heap with a new item and then compare link it with the original tree. Well, here's another example. Okay. This time I want to insert a 14. So I'll create a pairing heap with a single item 14, then compare link those 2 pairing heaps together. Since the 9 is smaller than the 14, the 9 will become the leftmost child of the 14. Okay. So again, order 1. All right, so the actual cost of an insert is order 1. Any questions about insert? Okay. All right, suppose we do inserts in this fashion, and actually there's going to be no extra work done, unlike Fibonacci heaps where we later came and started to do cascading cuts. That's all that we're going to be doing. So knowing how the insert works, we can arrive at bounds on the degree as well as height of pairing heaps. Okay. So suppose you insert items in this order, decreasing order. Okay. Well, then you'll first create a pairing heap that has a 9, okay, and then one with 8, and you'll compare link them, so 8 will become the leftmost child of 9. Okay. And then when the 7 comes in, it will become the new leftmost child of 9. And then 6 will become the new leftmost child of 9, and so on. So you're going to end up with, okay, so 8 becomes the child, then 7, and then 6, and finally up to 1. Okay. So again, you'll end up with a tree that has only 2 levels in it. If you put in a total of n items, the root will have n minus 1 children. Okay. All right, so unlike binomial and Fibonacci heaps, the degree here is not constrained by log of the number of elements. If you look at the height, okay, right, suppose you inserted items in the other order, increasing order. Okay. Right, so 1 goes in, you get a single element pairing heap. Then you bring in the 2, you do a compare link, 1 becomes a child of 2. Okay. Then you bring in the 3, the 2 becomes a child of 3. Okay. Then comes in the 4, the 3 becomes a child of 4. Okay. And so on. Okay. So the height of this becomes n. So as far as pairing heaps are concerned, they have the worst possible degree and the worst possible height. Okay. Yet from the amortized point of view, they give you good performance, where good here means logarithmic for all operations.
What if all elements are equal?
What if all elements are equal? The tiebreaker you can use is arbitrary. Just pick one and say it's bigger than the other.
So here we are using priority.
We're using, well, we're certainly using priority because when elements come in, when you do the compare link, you compare the priority of two elements, and the fellow with the smaller priority becomes the child of the fellow with the bigger one. In case of a tie, you take any one. But by value of the element, I mean the priority of the element. Okay. Right. Okay. All right, so the worst case height is n, the worst case degree is n minus 1, and you can't get any worse than that. Let's take a look at the increase key operation. Okay. So to increase the key, somebody has a pointer external to you, and they give you that pointer in the node, and they tell you how much to increase it by. Okay. And when you increase the value, as far as the subtree rooted at that node is concerned, it remains a max tree. Okay. The problem was with respect to the parent, your value might now become bigger than that in the parent. Okay. Unfortunately, there's no way for you to check that except when you are the leftmost sibling or the leftmost child, because you don't have a parent field. Okay. So since you can't check, what you do is you assume the worst has happened and you cut yourself off from your parent. Okay. So here you always cut yourself off from the parent, whereas in Fibonacci heaps you first do a check and you cut yourself off only if you have to. All right, so here you're going to cut yourself off regardless. All right, so I've been asked to increase the key at 4. Whether you've been asked to increase it by 0 or 1 or 10, it doesn't really matter, because there's no way for you to check that the new key you have here is bigger than your parent or is smaller than your parent. Okay? And there's no efficient way to check. Okay? Certainly you could follow pointers, left pointers, and come all the way here and then check. Okay? But we're not going to bother to do that. We're just going to detach. Okay. All right, so regardless of what you increase it to, that subtree is detached. You pull it out of its doubly linked list, and that's an order 1 operation. You do have to be careful if you're pulling out the leftmost fellow, for example, this guy. Okay. Then you have to change the child pointer in the parent so it points to the next fellow. Okay. All right, so we're going to detach. Well, once you detach, okay, then I will compare link with what's left and create a new tree. Okay. So in the compare link, you look at the 2 roots. The smaller root becomes the leftmost child of the fellow of the bigger root. Ties are broken any way you like. Okay. All right, so that's the sequence of steps. Okay. Any questions about how we propose to implement the increase key operation?
The constraint is that the amount cannot be negative, right?
The constraint is that, yeah, the value of the amount cannot be negative. And the reason you have that constraint, of course, is that if you decrease, okay, if you decrease the value, you can't ensure that you have a max tree. Okay, so if I give you a negative value for the amount, this could, for example, drop to 0, and then you have a problem with this subtree, in which case you've got to go downwards to fix that problem. Okay, and that increases the complexity. Okay, so as was the case for Fibonacci heaps, the requirement is the amount is a non-negative number. Okay. All right, other questions with increase key? All right, if you look at the complexity, I need to detach this fellow. To do the detach, since it's a doubly linked circular list, you can pull it out in order 1 time. Okay. If it wasn't a doubly linked circular list, we can't use the trick we talked about when we were looking at binomial heaps, which said copy from the forward fellow, because there are pointers external to the structure which say my 4 is sitting in this node. Okay. Similarly, there are pointers which say my 2 is sitting out here, and if you move the 2 from there to here, the external pointers become invalid. Okay. So we can't use that copy trick. You have to physically play with that node. Okay. And that's why we have a doubly linked list. Okay. All right, so you can detach in order 1 time. And then you have to do the compare link, which is another order 1 complexity operation. So the actual cost is order 1. Okay. So the meld, the insert, and the increase key operation all have an actual complexity of order 1. Now let's look at the remove max operation. Since we're dealing with a max tree, the max item is in the root. So I take that item and throw it out. And once you throw it out, you're left with a potentially large number of subtrees that have to be melded into a single tree. All right, so if it's empty, you got nothing. Otherwise, you take the root out, and you have to meld the subtrees into a single tree. And here is where you need to be careful about how you do the melding. If you do the melding using what we'll call a good way, then you can prove log n amortized complexities. If you do the melding in what we'll call a bad way, you can prove order n amortized complexity is the best. Okay, so I guess the trick, if you want to call it a trick in this structure, is how you do the melding of subtrees following a remove max, and also following an arbitrary remove, which we'll see in a moment. Now let's first take a look at a bad way. And for this, we'll see that the amortized complexity, the best provable amortized complexity, is order n. Okay. Right, so a bad way is, I've taken out the root, and let's say I'm left with 10 subtrees. So I pick one of these, let's say the first one, and make that the current tree, and then I'll go through 9 rounds of melding the remaining trees one by one into what's the current tree. Okay. So we start with the first tree, then for each of the remaining trees, do the compare link operation to meld the next tree into the current tree. That gives you the new current tree. Okay. And that seems to be the simplest way to do it. Also an intuitive way to do it. So for example, if this is your pairing heap, you do a remove max, the 9 goes out. Okay. When the 9 goes out, we're left with these subtrees. Okay. Then I take the 8, I meld the 6, compare link the 6 into it, then compare link the 4, the 2, the 1, and so on. Okay. So we'll end up with that. Okay. So you start with 8, compare link the 6 in, it becomes the first child. Then you put in 4, it becomes the new leftmost child. You put in 2, it becomes the new leftmost child, and so on. We end up with that structure. Okay. So the total number of compare links we had to do here, we were left with 2, 4, 6, 8. So I had to do 7 compare links. Okay. Now suppose you do another remove max. Okay. So you take out the 8. Okay. And then we'll start with 7. 5 will become its first child, and then 3 will become its new first child or leftmost, then 1, then 2, then 4, and then 6. Okay. So that's going to take 6 compare links. Okay. And the structure you're going to be left with after that, okay, is again symmetric to what you started with. Okay. Except you got 2 fellows less. You lost the 8 and you lost the 7, but you got the 6, 4, 2, 1, 3, 5. Okay. You do another meld, that's going to take you, I guess, 5 compare links. So you do another remove max, then you do one to take you 4, and so on. Okay. So if you look at this particular example, you do a sequence of remove maxes. Each remove max will take 1 less compare link than the previous one. Okay. So if you started with about n items in there, the first one might do n minus 1, then n minus 2, n minus 3, and so on. All right, so the actual cost of an insert. So let's say now we start at ground zero, you got nothing. Okay. And I'm going to do a bunch of inserts. Okay. And then after the inserts, I'm going to do a sequence of remove maxes. And then I'll take a look at the time for this whole sequence. Okay. So I'm going to do a bunch of inserts. Each insert is going to cost me 1. I'm also going to do a bunch of remove maxes. And the cost of each remove max is the degree of the root. Okay. So I'll do n over 2 inserts in this order. That'll give me the initial tree that I put up. Okay. So I expand that sequence so that it's of size n over 2. Okay. And then I'll do n over 2 remove maxes. Okay. Right, so this example is for the case where n is, I guess, 9. Yeah. where n over 2 is 9, so n is 18. Okay. And here n is the total number of operations in the sequence. Okay. Right, so n is 18, n over 2 is 9. I do 9 inserts. That gives me the tree I had up before. Then I'll do 9 remove maxes, bringing it down to an empty tree. Okay. So the inserts cost you 1 each. I'll do n over 2 of those using the expanded version of that sequence. That cost me n over 2. Then I'll do my n over 2 remove maxes. The first one will cost me n over 2 minus 1, because that's the degree of my tree. Okay. So for example, here the degree of the tree is 8, even though there were 9 items or 9 inserts. Okay. So the first remove max will cost me n over 2 minus 1. The next one will cost me n over 2 minus 2, then n over 2 minus 3, and finally down to 1 for the last one. Okay. Right, so the cost of the remove maxes works out to be theta of n squared. Okay. So from this example, what you see is that if you claim that the amortized cost of an insert is 1, okay, then the only way you can end up with a total sequence cost of n over 2 plus n squared is if the amortized cost of a remove max is n, of order of n, some constant times n. Okay. So if the amortized cost of an insert is order 1, then the amortized cost of an insert max, of a remove max, has to be theta of n. And since we claimed that, right, similarly, if the amortized cost of an insert is log n, okay, then the n over 2 inserts only give you n log n. The only way to get n square is if the amortized cost of a remove max is n. Okay. Similarly, if the amortized cost of a remove max is log n, the amortized cost of an insert has to be n. Otherwise, you can't get the n square total sum. Okay. All right, so from this example, what we see is that one of these two operations, the insert or remove max, has to have an amortized cost that is order of n. Otherwise, you can't pay for the total n square cost. Okay. All right, any questions about that? Right, so if we handle the remove max in the way we just did, you simply are not going to have a structure that has an amortized complexity of order n for each of the operations. It's got to be order n for at least the insert or the remove max. Okay. All right, so that way of doing a remove max isn't any good. Right, there are several good ways to meld these trees, which give you, which allow you to prove log n amortized complexity for each of the operations. We'll take a look at two of them. The two-pass scheme and the multi-pass scheme. Doesn't matter which one you use, the best bounds known are log n for all of the operations. The experimental results seem to indicate that the first of these gives you slightly better performance in terms of actual measured runtimes. Let's look at the two-pass scheme. So in the first pass, you examine the subtrees that you have. So you take out the root, you're left with a bunch of subtrees, examine them from left to right, and meld pairs of them together. So you compare link pairs of them, and that reduces the number of trees to about half. Okay. In case you have an odd number, then you take the remaining fellow and compare link it into the last fellow you had from this step here. Okay, we'll look at an example to make clear what we're doing. Okay. Once you've reduced the number of trees to half, then you run the bad scheme, essentially. Okay. So you take the rightmost subtree generated here, call it the working tree, we were calling it current tree, and then meld the remaining fellows into it one by one. Okay. So the main difference between this and the bad scheme is that you have a pre-pass where you cut the number of trees to half by melding them in pairs. And then you run essentially the bad scheme. Okay. Let's look at an example. Okay. So let's suppose I've got 8 trees. Okay. So I'll compare link the first 2 together. I'll compare link the next 2, the next 2, and the next 2, reducing the number of trees to half. If I had a T9, I would compare link the T9 with S4 at this time. Okay. So again, you'll end up with half of the number of trees, or a little bit less than half. Okay. All right, that's the first pass. Okay. In the second pass, you take a look at the results from the first pass. You start with the rightmost fellow, compare link it with the fellow before it. Okay. Then you compare link it with the fellow before it, and compare link it with the fellow before it. Okay. All right, so that's the 2-pass scheme. Any questions about the 2-pass scheme? All right, again, there's nothing really intuitive about it. What was intuitive was the bad scheme, but the bad scheme is bad for a good reason. It's got bad amortized complexity. Okay. Here, again, why do you do it this way? Well, the only reason to do it this way is when you do it that way, people can prove that the amortized complexity is logarithmic for each of the operations. All right, the multipass scheme. All right, this looks a lot like the way you would, say, initialize a leftist tree. Okay, if you recall, what we were doing there was you start with n elements, you create one element leftist trees, toss them into a queue, pull them out 2 at a time, combine them into one, meld them into one, put them in the back of the queue. We're going to do the same thing out here. Take our trees, toss them into a queue, pull them out 2 at a time, compare link, put them in the back, keep doing this till you're done. Okay. All right, so take the trees left after you toss out the root, toss them into a queue, and then we have a step that gets repeated till you're left with a single tree. You pull 2 trees from the front of the queue, compare link them, put the result into the back of the queue. Okay. So each iteration of this reduces the number of trees by 1. If you started with 10 trees, after 9 trees, you'll be left with 1, and you're done. Okay. All right, so say I've got 8 trees. Put them in a queue. I pull out T1 and T2, compare, meld them, get S1, put it in the back. Pull out T3 and T4, compare, meld them, get S2, put them in the back. Pull out 2 from the front, T5 and T6, compare, meld them, compare link, you get S3, put it in the back. You pull out T7, T8 from the front, compare link, you get an S4, put it in the back. Okay. Now if you had an odd number, say T9, you would take T9 and compare link it with S1. Okay. Once you've tossed them in the queue, you just repeat that basic step, pull out 2 at a time, compare link or meld, and put the result in the back. So now you pull out S1, S2, meld or compare link, put in the back, pull out S3, S4, get an R2, one more steps needed, pull out 2, put back 1, and you're done. Okay. All right, so that's the same as how we were initializing leftist trees. Again, here, there's a proof around that shows that if you do your recombining of the trees that are left following the remove max, throwing out the root, the amortized complexity is log n for all of the operations. Okay. The actual cost is order n because the degree can be as much as n minus 1. So you throw out somebody, you got degree n minus 1, you got to look at all of them. That's order of n time. All right, we have one operation left. That's to remove an arbitrary element. If it's the root, you handle it like you're doing a remove max. If it's not the root, we need to handle it differently. Okay. So we take it out of its doubly linked list of siblings. And when you take it out, you got to throw away the node itself, so that gives you a bunch of subtrees that it had. We need to combine them together into one, so we'll do that either using the 2-pass or the multi-pass scheme. Okay. So whatever strategy you adopt for the remove max, we'll adopt the same one here. And after you've done that, we'll meld it with whatever was left after you pulled it out from the main tree. Okay. Let's look at an example to illustrate how this works. All right, so I've been asked to take this item and throw it away. The way I'm going to do that is I'm going to pull this whole tree out of its doubly linked list like I did for an increased key. However, in an increased key, the number of elements didn't change. We didn't have to throw the node away. Here I got to throw the node away, and that's going to give me these 2 subtrees. Okay. All right, so take it out of its doubly linked list. That's an order 1 operation. You get that. Then we're to take the root and toss the root away, and that's going to leave me with some number of subtrees, which could be of the same order as the total number of elements or total number of operations you've done so far. Okay. And then in this case, I'll be left with 2 subtrees. I'm going to combine them into one using either the 2-pass or the multi-pass scheme. In this particular case, it doesn't matter which scheme you use. There are only 2 trees to combine. You get the same result. So we end up with that. And once you've done that, we'll then meld this with the big tree, whatever, okay, this fellow here, to end up with a single tree. So you do a compare link. The 3 is smaller than the 9, so it's going to show up as the leftmost child of the 9. All right, questions about removing an arbitrary element, given a pointer to the node which has it. Okay. All right, the actual complexity of this is order n, mainly because when you threw away the node, it could have order of n children. Okay. So unlike the increase key, which was order 1, this is an order n operation. Okay. Any questions? Yeah.
Question about the previous one. Good way and bad way.
Yeah.
What is the difference between good way and bad way?
What's the difference between the 2 in terms of why one is called good and one is called bad, or the mechanics?
Anyhow, we are the number of comparison are not reduced.
All right. Question is. What's the difference between the good way and the bad way? If you're looking at an individual remove max operation, okay, so that individual remove max operation takes the same amount of time, whether you do it the good way or the bad way. It's the same number of compare links. Okay. The difference comes about when you try to establish an amortized complexity. So you look at a sequence of these. For the bad way, the example we saw showed that there's no way anybody can prove the amortized complexity is logarithmic because it isn't. Okay. The amortized complexity for the insert or the remove max, one of these two operations has to be order n. Okay. So for what I call the good way, using either the multipass or the two-way, there are proofs around which show that the amortized complexity is log n, which is the same as saying that no matter how hard you try, you will not be able to come up with an example where the cost of a sequence of n operations is n squared. Every sequence of n operations will take n log n time. Okay. Now we haven't seen the proof, so it's kind of hard to maybe convince you mathematically of that fact, but there is a proof around. Okay.
Where can I get that proof?
Well, where can you get the proof? If you check the readings, there's a citation to the original paper that developed pairing heaps. So if you pull out that paper, it's got the whole proof there. Okay. Certainly, if you go to the web and do a Google search, you'll probably find more recent proofs that may be simpler than the original proof. Okay. All right. Any other questions? Yeah.
So, in a pairing heap, once a node becomes a child, the software within that particular node does not increase in size. Is that correct?
Well, once it becomes a child,
The software within that particular node, the size of that software
okay. So once a node becomes a child, then its subtree does not increase in size. Well, it depends on the operations you do, because you may end up pulling it back out from the top level tree later when you do a remove, and eventually it could, through changing keys, show up again somewhere else. Okay. So if it doesn't ever show up as the root again, then its size can't change.
And what's the application of this particular?
What's the application? The application is the same as Fibonacci heap.
But you don't have the reduced key operations.
Oh, I don't have the reduced key. That's because I looked at the max version. If I change it to the min, then it becomes a decreased key. Okay. Yeah. So really the question becomes, what's the application of Fibonacci heap? Because this performs better than Fibonacci heap. Okay. and so in reality, you're going to get better performance than this if you believe all the experiments that have been done. Okay. The Fibonacci heap then becomes a theoretical structure for which you can prove a good bound, but which doesn't perform as well as the Fibonacci heap. Okay. All right, so we'll stop here.